Hi, my name is Lucas, and I study nuclear fusion at the Eindhoven University of Technology. Fusion reactors are complicated. In order to achieve fusion in the first place, we have to produce an extremely hot and dense plasma with a temperature of over 100 million degrees. But then we also need to keep this plasma in one place for long enough that we can actually extract the energy out of it. And we can do this using very carefully tailored magnetic fields and very complicated looking field coils. But due to a little quirk in the geometry of the system, this plasma is going to fight back. Now, in order to trap a fusion plasma, we are going to need to build a magnetic cage. And for practical reasons, this cage needs to be toroidal in shape. But it turns out that you can't actually confine a plasma in a purely toroidal magnetic field. No, what we need is a helical magnetic field. And there are two main ways in which we can build such a magnetic field. For one, you can build a tokamak. In this case, you'd use toroidal field coils to produce a toroidal magnetic field, and then you drive a current in a toroidal direction to get that remaining toroidal field component. And the benefit of this setup is that it's relatively simple, but its downside is that the tokamak can't always be online, and also the current can destabilize the plasma. Alternatively, you could build a stellarator, in which case you'd use coils alone to build magnetic fields. And this way you avoid both of the issues we mentioned for tokamaks, but as a result, the geometry of the coils is going to be a lot more complex. Now, these models are cool and all, but the real deal is right behind these doors. So while we're making our way in there, I'll have somebody who knows a bit more about stellarators do the talking.
Hi, my name is Samuel Lazarson. I'm a research scientist at the Max Planck Institute for Plasma Physics. W7X, or the Wendelstein 7X experiment, is designed to demonstrate the HELIAS line of stellarator reactor concepts. It is a prototype in some sense on the way to a full HELIAS reactor. It's designed to show many of the key features and technologies required in an actual reactor. Optimized stellarators have a lot of advantages compared to tokamaks. The primary one is that they don't require current drive. So they have no transients and there's no possibility of a catastrophic failure of the device. In addition, they don't need any of the auxiliary current drive mechanisms or techniques that tokamaks need. The disadvantages of a stellarator are in their upfront costs. In order to get a stellarator to perform at or better than a tokamak, you have to spend a lot of time engineering and predicting the design of your system.
Underneath all this scaffolding is the Wendelstein 7X stellarator. Now, between tokamaks and stellarators, when it came to which of these would make a better fusion power plant, stellarators have historically been considered a bit of an underdog. And the reason for that is because they suffered from what's called poor neoclassical confinement. But as computing power has improved over the years, it has become possible to design stellarators which have improved confinement. And Wendelstein 7X is one such optimized device. One problem faced by W7X are currents.
So the main current that we tend to see in W7X is known as bootstrap current. And this occurs through a friction between ions and electrons streaming past each other, and the strange orbits that these particles can make when they're not just simply following the magnetic field. When we look at the bootstrap current in, say, a tokamak, what we have is an axisymmetric bootstrap current. So it goes in a direction that improves confinement. So it twists the magnetic field more. When we have a helically symmetric device, what we find is that that bootstrap current goes in the opposite direction.
So in short, currents unravel the magnetic field. And so we want to avoid currents in future W7X-like reactors. But in order to avoid something, we have to understand it first. And there are two key aspects that we have to consider. The first aspect is, what does the current want to be? And in many cases, this boils down to, what is the bootstrap current? And we have many different numerical models that we can use to calculate that. But there's a trade-off between speed and accuracy. On one end of the spectrum, we have something like Sphinx, which is a very complete physics model, but to calculate the bootstrap currents can take hours. And on the other end of the spectrum, we have something like BootsJ, which can do the same calculation in mere minutes, but its assumptions aren't always valid. The second aspect we need to consider is, how does the current actually get to this value? You see, as the current changes, it changes the magnetic field. And because the magnetic field is changing, we're going to see an electric field appear in the plasma. And this electric field will slow down the evolution of the current.
But because the plasma is conductive, but not infinitely conductive, it takes some finite amount of time for these currents to actually establish themselves in steady state. So for periods of up to around 30 seconds during a discharge, the plasma currents can be evolving and changing in the discharge.
And this last aspect is not really well understood. Or rather, we know how the total current should evolve, but we don't know how the current density or distribution of currents should change in time. And on top of that, as the total current changes, the magnetic field changes. And as the magnetic field changes, the bootstrap current itself will also change. And so we have this really complicated interplay between the total current, the bootstrap current, and the magnetic field that we somehow have to take into account. And this is where Thrift comes in. So Thrift is a code written in the early 2000s that was designed specifically to model the evolution of the current in a way such that the total current, the bootstrap current, and the magnetic field are all consistent with each other. But what we realized only recently is that we can actually use Thrift to verify whether our models of the bootstrap currents are accurate. And so in this project, for the first time ever, we've actually used Thrift for this purpose. So we have rewritten Thrift using more modern standards. We then used Thrift together with BootsJ to simulate a few different experiments in W7X. And then we've actually compared these results to what was actually being measured in experiments. And what we can see so far is that we can get the evolution of the total current correct, but the magnitude of the current that we see in our simulations is way smaller than what we actually see in experiments. And so what we can infer from this, for example, is that the model of the bootstrap current that we used, so BootsJ, isn't accurate when we try and apply it under these conditions. Now, in this project, we've only looked at one bootstrap model. Honestly, most of the time has just been spent on getting Thrift to work. But what's most exciting though is what we can now do with Thrift. What we've basically shown is that Thrift works the way we thought it would. And we can now go and play around with different bootstrap models and benchmark all of them. And it's important to do these kinds of tests, because if you want to make sure that our design of a fusion reactor has low bootstrap currents, like we would want, then we need models that we can trust will give accurate predictions. And not just models of the bootstrap currents, but also models for any kind of current that we drive in the plasma. So neutral beam current drive or electron cyclotron current drive. Having good models for all of these is absolutely necessary if you want to try and design scenarios in future reactors. And Thrift gives us a new way to validate all of them. Like I said at the beginning, fusion reactors are complicated. There's still much that we don't know. But through experimentation and modeling, we are slowly filling that gap. And eventually, if we continue on this path, we'll figure out how to build fusion power plants that will help us solve the energy problem of the future.